Okay, we are live, sir. Okay. A very warm good evening to all of you, those who have joined from India, and good afternoon and good morning for those who have joined in from other countries. I'm very happy to welcome you for this second series of inspiring talks by Inspired Minds. And my name is Vinay Nair. I'm the founder of Vichar Vatika. Let me just take a couple of minutes to brief you about what we do and brief about this series of talks. So we are into equipping students with better mathematical tools to solve problems, if I have to put that in one statement. And there are different programs that we do for school students, namely Ganit Manthan, Ganit Krida, and Math Excellence program. And of the three, Ganit Manthan is a course that runs throughout the year for students who are precocious and passionate about mathematics. And this series, Inspiring Talks by Inspired Minds, is a series of talks, monthly series of talks by students who are part of the Ganit Manthan program. And what I normally see with these students is that they are not just passionate about mathematics, but they are equally passionate about other disciplines, if not more. So if you would have seen our YouTube channel, you would have seen last month's talks by Siddharth, Nidhi, and Adrit, who spoke about physics and astronomy, genetics, and arthropods. In case you haven't seen, I would highly recommend you to watch it on our channel, and I'll share the link in the chat. And without any further ado, let me introduce our first speaker for today. Johan, can you switch on your video? Right. Our first speaker for today is Johan Philip. And Johan is a 10-year-old math and science enthusiast. He lives in Tiruvalla, Kerala. Apart from mathematics, he loves coding and he's a great swimmer. He has also represented his school team for swimming. He plays the keyboard and he also enjoys solving puzzles. And when he's free, he loves to explore numbers, tries to find patterns in numbers, and he explores more and more patterns in numbers. And apart from all this, he is passionate about astronomy, and he is hopeful that one day he'll visit Mars and explore the planet. And I'm sure that day is not very far away. Johan, we are very happy to have you as the first speaker of this second series. And over to you, Johan.
Okay, sir. Okay. Okay. Good evening, Vinay sir, guests, and my dear friends. Today I am here to do my presentation for Inspiring Talks by Inspired Minds on black holes. Black holes. This is a news clipping from the Times of India newspaper. On the 30th of June 2021, scientists detected gravitational waves from a neutron star and a black hole collision. Indian researchers were also a part of this finding. Have you ever wondered what exactly is a black hole? That's what we're going to find out in this presentation. What is a black hole? A black hole is a place in space where gravity pulls so much that not even light can get out. Anything that goes too close to a black hole, a star, a planet, or maybe even a spacecraft, will be stretched and compressed like putty in a theoretical process aptly known as spaghettification. Now let us explore the characteristics of a black hole. A black hole's gravity is very strong because a lot of matter has been squeezed into a very tiny place in space. In other words, a black hole has a very high density. They are also invisible because light around a black hole is absorbed by the black hole, and so none of the light reaches our eyes and we can't see it. This is an artist's drawing of a black hole named Cygnus X1, the first black hole ever discovered. Elements of a black hole. An accretion disk is a swirling mass of matter destined to spiral into the black hole or be ejected into space. However, not all black holes have these. Relativistic jets are jets of matter and radiation that extend out to hundreds of thousands of light years. But even these are not found commonly on black holes. But one thing that is found on every black hole is the event horizon, the gravitational boundary beyond which neither light nor matter can escape. How big are these black holes? Black holes can be big or small. Scientists think that the smallest black holes are the size of just one atom, but these have the mass of a large mountain. Stellar mass black holes have masses of around 20 suns. That is, stellar mass black holes have masses of 20 suns put together. On the other hand, supermassive black holes have masses of from 1 million suns, which is a lot. Sagittarius A star is the supermassive black hole at the center of our galaxy. It has the mass of 4 million suns and would fit inside a very large ball that can hold many millions of Earths. Now let us see what are the types of black holes. There are 4 types of black holes. The first one is the miniature black hole. The second, stellar mass black holes, intermediate mass black holes, and finally, supermassive black holes. Stellar mass black holes. They are formed when a single massive star runs out of fuel. The smallest stellar mass black holes have masses of more than 3 times the mass of our sun. They are spread throughout the Milky Way galaxies and other galaxies in our universe. An example is Cygnus X1, the first black hole ever discovered. This is an X-ray image of Cygnus X1 taken by NASA's Chandra X-ray Observatory. Supermassive black holes. Supermassive black holes are formed when many enormous black holes combine into one enormous black hole, superenormous. They have masses of from millions to billions of times the mass of our sun. They are found at the centers of galaxies. An example is M87 star in the heart of the Messier 87 galaxy. The first optical image of a black hole taken by the Event Horizon Telescope was one of M87 star. Intermediate mass black holes. They are thought to form when multiple stellar mass black holes undergo a series of mergers with one another. But that is not the only hypothesis for the formation of intermediate mass black holes. There are 2 others. One is the runaway collision of stars in a dense star clusters, with the product collapsing into an intermediate mass black hole. The other one is that intermediate mass black holes are primordial black holes. Primordial black holes are black holes formed soon after the Big Bang. Intermediate mass black holes have masses of 100 to more than 10,000 solar masses. One solar mass has the same mass as our sun. On the 21st of May 2019, the National Science Foundation's Laser Interferometer Gravitational Wave Observatory, or LIGO for short, detected gravitational waves from the merger of 2 black holes. The resulting black hole, the gravitational wave event dubbed GW190521, resulted in a black hole weighing 142 solar masses, thereby it being classified as an intermediate mass black hole. And finally, the last kind of black hole. This kind of black hole is purely theoretical, the miniature black hole. They are thought to have formed from dense spots in the early universe soon after the Big Bang, then quickly evaporated. In other words, they are also primordial black holes. They have a minimum mass of about 10⁻⁸ kilograms. Since these are purely theoretical, we are yet to find an example of one. Now let us see how black holes are formed when black holes are formed. Scientists think that the smallest black holes formed when the universe began, and that supermassive black holes were formed at the same time as the galaxy they are in. A star uses hydrogen as nuclear fuel in a process known as nuclear fusion. In nuclear fusion, two hydrogen atoms combine into one helium atom. Now, this process releases a lot of energy, which pushes outward on the star. At the same time, gravity created by the mass of the star is trying to pull the star inward. Most of the time, these forces balance. But at the end of a star's life, when it runs out of hydrogen, it can no longer generate that outward push. So gravity wins and the star collapses into a black hole. If black holes are black, how do scientists know they're there? Earlier, we answered why we can't see a black hole in the first place. Because light around a black hole is sucked into it, and so none of that light reaches our eyes. So how do scientists see a black hole? One way is to use satellites and telescopes in space to detect high energy light created when a star and a black hole are together. Another way is to study stars that are flying around or orbiting a seemingly empty place in space. But that place is probably not empty. It could be the place where the black hole resides. All this talk about black holes could have raised the question in your heads. Could a black hole destroy Earth? Fortunately, the answer is no, because no black hole is close enough for Earth for that to happen. But what would happen if there was a black hole with the same mass as the Sun in the Sun's position? Nothing would happen, because if that black hole had the same mass as the Sun, it would also have the same gravitational force of the Sun. And so the planets would keep on orbiting that black hole as they do orbit the Sun today. But will the Sun ever turn into a black hole? Thankfully, no, because the Sun is not a big enough star to turn into a black hole. We just discussed the question of if a black hole could destroy Earth. But can a black hole be destroyed? Yes, due to something known as Hawking radiation. Hawking radiation works because empty space or the vacuum is not really empty. It's actually a sea of particles popping in and out of existence. If such a pair of particles is formed near the black hole, there is a chance that one of them will be pulled into it. In this scenario, the other black hole escapes to space. The energy from the escaping comes from the black hole, and so the black hole slowly loses energy and mass by this process. But it would take more than the entire age of the universe for most black holes we know about to significantly evaporate. Black holes, even the ones just a few times the mass of the Sun, will be around for a really, really long time. Can someone identify the person in the picture, in this slide?
The answers can be put on chat.
Yes,
answers are
it's
coming
Stephen
in.
Hawking. It's Stephen Hawking. Stephen Hawking first theorized Hawking radiation. Okay. X-ray binaries. A spectacular set of rings has been found around a black hole in a binary system called V4O4 Cygni, located about 7,800 light years away from Earth. A light year is the distance light takes 1 year to travel. Or in other words, light travels a light year in 1 year. This black hole is actively pulling material away from a companion star. The star has a mass of about half the mass of the Sun. The entire thing glows in X-rays. So these kinds of binary systems are known as X-ray binaries. Let me show you something interesting. Okay. You can see the constellations Virgo and Leo. Now you can see this beautiful dark background against which tiny pinpoints of light stand out. Now we are now zooming in to the elliptical galaxy Messier 87. You can see it looks like a little egg, little white egg. Now as we are zooming in, you can see this red gas cloud. At the very heart of all this, we will find M87 star, the first black hole ever to be taken an optical picture of. The Event Horizon Telescope took an optical image of this the Event Horizon Telescope took an optical image of this black hole. The first ever optical image. These are my references. The Theory of Everything is a book written by Stephen Hawking that answers many questions about the universe and black holes. Thank you.
Thank you so much, Johan, for that wonderful presentation. It was really very inspiring, and I almost got a free tour into space. I'm sure others also would have felt that way. So this is to the audience. If you have any questions that you would like to ask Johan, you can do a raise hand and we can unmute you and you can ask your question directly. All right, there are hands raised immediately. So I'll start with Smayan.
Hello, can you hear me?
Yeah.
Yeah, so my question is, how do you take the image of the optical image of the black hole, the first black hole that was created, that we took an image of?
Yeah, I actually expected this picture because this question because everyone would be thinking, if light cannot escape from a black hole, how can you take the picture? Yeah, so when matter is falling into the black hole, it's accelerated into very high speeds. Now, when it's accelerated into very high speeds, all this gas starts glowing. So if the light doesn't touch the event horizon, that gravitational boundary, it can escape. The escape velocity is low enough for it to escape, and so we can take the image of this.
Okay. So essentially some light escapes and it highlights the black hole.
Exactly.
Okay. Yeah, thank you.
Adrit.
This is a question related to Smayan's question, I think. How would the satellite know how to aim at before the event horizon? I mean, it being more than several light years away. It's not very easy to take a picture of it like that.
Yeah, so they don't use satellites in space to take optical images of black hole. They used lots of telescopes on the ground. The Event Horizon Telescope is virtually a telescope the size of the Earth, because you have radio telescopes situated all around the Earth. So you take into account whether
so they put the radio waves into one specific spot and they concentrated that to take a picture.
Yeah, something like that. You use optical telescopes as well to try to find this light. You see if the weather is good and if the Earth is oriented in the correct position, and so you can try getting optical light, that is light that you can see with your eyes from black holes.
Wait. Okay, so now they had to wait several months for the Earth to be positioned in a specific way.
Yeah, sometimes. I mean, when they were trying to take the first few images, you had to align it properly, right? Only if you align it properly can you take a good image.
Okay.
It's like a camera. You don't put it in the correct way, you won't take the image you want. It's the same thing. It's like a cosmic camera.
I got that.
Okay, moving on ahead to the next person, Siddharth.
Johan, can you explain again what is Hawking radiation?
Okay, so you've heard of the vacuum, right? Empty space.
Yeah, I've heard of vacuum.
Yeah, so sometimes virtual particles, so there are these little particles that just pop in and out of existence. So they always come in pairs, okay? So if one of these pairs is formed near the black hole, one of them could be sucked into it, the black hole. The other one will escape into space. I mean, escaping into space certainly takes some amount of energy. The black hole provides the energy for that. And so in the formula E equals mc squared, if you lose a little bit of energy, you lose a little tiny bit of mass. So it's like that. You lose enough energy and you lose enough mass for the black hole to like shrink and disappear.
Oh, okay, I get it. Thanks.
Okay.
Vagisan.
Okay, so my question is like, how is it like possible to like see how is the black hole discovered?
Sometimes these kinds of black holes called quasars. No. Okay, so these kinds of black holes, they don't. It's not. I already covered that. So one way is by measuring the high energy light, like gamma rays and X rays created when a star and a black hole are close together, right? Okay. Another way is to see stars that are orbiting an empty place that could contain a black hole.
Okay, like I'm telling like who how was it discovered? Like who discovered it? That
Oh, that kind of information. You mean Cygnus X1, the first black hole ever discovered?
I'm telling like who first discovered a black hole and who discovered like and came up with the theory of a black hole.
Oh, that I'm not really sure. It actually goes a bit of a long way ago. It came a lot. They thought of it long time ago. So
Okay, got it.
I'll have to get more information on that.
Okay, Shabarish and Radhika.
Yeah, thank you, Johan, for the very informative talk. So it is not a question, it's just a additional info. So you may be knowing like LIGO, you are mentioning about LIGO, laser interferometer for gravitational wave observation.
Yes.
So there are four such facilities already in operational all over the world. Two in LIGO Livingston and LIGO Hanford. One LIGO Virgo in Italy and Gagra in Japan. And the fifth one, we are fortunate that we are going to have it in India. It is very close to or between Pune and Hyderabad in a place called Hingoli. And the researchers are working on that and it is expected to be operational by 2024. Just since you are mentioning on LIGO, I just thought I'll add.
Yeah, okay. Thanks for the info.
Thank you.
All right. So it looks like there are no further questions. So I'll just end this with one question that I have to you, Johan. So who is the scientist that you admire the most? Who's your hero, and why?
In what topic? Because I have a lot of scientist admirers in different topics.
Okay, so if it's a general thing, who's your favorite? I mean, anyone who you want to name?
Stephen Hawking.
Why?
Because he figured out black holes, he figured out Hawking radiation, he figured out lots of stuff, like the universe had to be spherical and stuff. He thought of the spherical, he thought of how the universe would end and how the universe, he was one of the supporters of the Big Bang theory. So how could I not resist having Stephen Hawking as my admirer?
Good one.
Yeah.
And what's your plan further down? How are you planning to continue your study into black holes, or is there any place that you are stuck with in lack of resources, or you would be looking forward to getting some assistance or help from people? I'm asking this question so that amongst the viewers, if they have any suggestions, if they have anybody whom they can connect you to, you can, you can get connected to such people. So anything on that front?
Not really.
All right. Okay. So thank you, Johan, once again. Wonderful presentation and taking us into space and bringing us back to this virtual floor. So viewers, the chat is open for you to put your comments about Johan's presentation if you would like to. And from here, we will move on to the next speaker. All right, Bhagavat, can you switch on your video? Yes. So we have our second speaker, 11-year-old Bhagavat from Hyderabad. Bhagavat is an avid reader and he loves to read all kinds of books, both fiction as well as non-fiction. And apart from mathematics, he loves English, he loves history, he loves drawing, he plays the veena, and he's also passionate about the martial art form karate. And over a period of time, he got interested in cryptography and he started reading more about the subject. So in this talk, Bhagavat is going to share about some amazing aspects that he gathered about cryptography over the past few months. Over to you, Bhagavat.
Yes, thank you, sir, for the introduction. So, am I audible?
Yes.
Yes. So, is my screen visible?
Yes.
So, good evening, everyone. My name is Bhagavat. So, today I'm going to present to you my talk on cryptography. So, today I'll be discussing about mainly about 4 WH questions. So, what is cryptography? When did people start using cryptography? How is it used? And what is the relationship between mathematics and cryptography? So, I'll also include some crazy and cool facts also on cryptography. So, with a humble note, this content is based on the perspective of a school kid, so not much will be available. So, let's now start our journey to the land of cryptography. So, what is cryptography? So, basically, cryptography is the study of sending secure and safe messages. So, it's also the method of protecting information using communication using codes. So, basically, there are 2 types of cryptography which uses keys. So, those are symmetric key cryptography. The first one is the symmetric key cryptography. So, basically, in symmetric key cryptography, both the sender and receiver share a single key. So the sender uses this key to encrypt the message, and then he'll send the ciphertext or the coded message to the receiver. The receiver applies the same key the sender uses, and he decrypts the message and recovers the plain text. So any third person might not hack it because he or she might not have the another key which both the sender and the receiver possess. So the second is the asymmetric key cryptography. So you can imagine it like this. So there's a home and there is also a letterbox. So every day the postman comes, open the lid of the letterbox and then puts in the letter. But then he cannot access the letter from inside of the house. So what do? We open the lock so we can open the lock and then we take out the message. So that way, so the postman is the sender. So he has one public key, so which is available to contacts of the receiver, and the receiver has the private key, which has all information about personal information like bank transactions or Gmail or email account passwords and etc. So only the receiver can access his messages and the private information, while the sender can only send the message but cannot access any private information. So I consider this asymmetric key cryptography more safer than the symmetric key cryptography. So along with asymmetric key cryptography, another function which does not use keys is used. So it's basically called as the hash function. So in this, any plain text like, let's see, hello, is converted into a long series of numbers and letters. So I converted into a series of letters based on their placing in the alphabetic order, and then the receiver applies the asymmetric key cryptography. So he uses his own private key to decrypt it. So when it's being sent in the form of this coded message, any third person can only receive it as the coded message, even if he manages to hack through it. So this coded value is called as the final value or the hash value. So the term cryptography derives from the Greek words cryptos, meaning hidden, and graphias, meaning writing. So cryptography uses very hard codes. So for example, in a common man or layman's term, potatoes mean a vegetable. But while in the term of an Enigma cryptographer during the World War II, it may mean grenades. So many sets of mathematical algorithms are used to encrypt a coded message in cryptography. So these army personnel, they use the cryptography in mathematical form to crack open codes which may mean threat to their country or to send encrypted messages to their databases, to their bases. So these are some of the features of cryptography. So I'm not getting into much detail. So those are confidentiality, the messages have to be secret, integrity, they have to be non-corrupted. Then there is a process called as authentication, in which the user will be identified, and then there's also another process or assurance called as non-repudiation. So someone cannot deny that he or she sent the message, or he or she did not send, or he or she received or did not receive. So let's see how in the olden times people used cryptography and why. So the art of cryptography is believed to have come along the art of writing. So ancient civilizations all used forms of message concealments in peace and war. So the earlier people used methods called as ciphers to encrypt and decrypt messages. So the surprising fact is that ciphers are even used nowadays. So the Egyptians used disordered hieroglyphics. The Greeks used another form of cryptography called as steganography. Then the Spartans used skytail ciphers. So the Romans used the Caesar shift cipher, and even we Indians use cipher devices such as Kautilya Mulavedya and the Katapayadi numeric system. So let's see how the Egyptians used hieroglyphics. So these disordered hieroglyphics date back about 4,000 years ago. So in this, each picture was replaced by a different picture for communication between two Egyptian rulers or pharaohs. So one of the most popular historical artifact which uses hieroglyphics is the Rosetta Stone. So it was found in 1799 by Napoleon Bonaparte's soldiers. So it was written in three ancient languages: Demotic, which was an ancient Egyptian language, hieroglyphics, and Greek. So it basically praised King Ptolemy V, the king of Egypt. So these disordered hieroglyphics were also called as simple substitution ciphers. So in which each picture was replaced, or each letter was replaced by a different letter. So some simple hieroglyphic codes are, so an image for a lion stood for the letter L, an image of a bird stood for the letter A, a square for the letter P, and So the Greeks used another form of cryptography which was very advanced. So it was called as steganography. So it was in this process, basically non-ordinary messages were hidden in ordinary sentences or pictures. So the first believed mention of the use of steganography is when Herodotus, so he was a Greek writer, so he narrated two steganographic messages in his stories. So he marked the name steganography. So another recorded use of steganography was in the year 1499 by Johannes Trithemius. So in his book called as Steganographia, he uses a form of he uses cryptography and steganography, but the book was disguised as a book about magic. So let's see how we Indians use cryptography. So we Indians use many different kinds of cryptography. Some of them were the Kautilya cipher, the Mulavedya cipher, and the Kattapayadi system. So, and great example of the Mulavedya cipher is in the incident of the great Indian epic, Mahabharata. So, Duryodhana was planning to burn the Pandavas alive and had also made arrangements to send Pandavas to Varnavata, where a house made up of inflammable substances were being prepared. So, Vidura learnt of the plan and resorted to talk secretly and warn Yudhishthira about the conspiracy. So he talked in front of everybody present in a cryptographic code. So it was the dialect called as Malecha. So none other than Yudhishthira could understand the coded message. So no one else thought it was a very great one. So let's see how cryptography became most popular in the term of World War II. So cryptography was used very extensively during the years of World War II. So the most popular of the cipher devices used during the World War II was the Enigma. So Enigma used very difficult codes in codes. So basically, for example, in the term of a common man or layman, a turtle basically meant an amphibian, while in the term of Enigma, a turtle means tanks. So around December 1932, Marian Rejewski, so he was a mathematician and cryptanalyst. So a cryptanalyst is a person who breaks cryptographic codes. So Marian Rejewski worked at the Polish Cipher Bureau, and he used the theory of permutations in which he counted the number of possibilities the code could be arranged in, and he finally broke the Enigma code. So another great personality who broke the Enigma code was Alan Turing. So he was a British cryptanalyst, and he built a machine or a cryptanalyst machine called as Bomb to break the code of Enigma. So some people think that by cracking this Enigma code, Alan shortened the war by 4 years and saved about 14 million lives. So then the Japanese used another secure cipher device called as Purple by the US Army. So in another cryptanalysis project called as Magic, the US Army broke the code of Purple. So let's see, how do we use cryptography nowadays? So you may have observed that always a message pops up in WhatsApp saying that our calls and messages are encrypted. So they basically mean that our calls or messages cannot be hacked by a third personality. So email clients. So those are people who use email. So we are email clients. So we use cryptography, though unknowingly, to secure our passwords. So in the Google Chrome browser, when we log into a website while signed into Chrome, so the Google Chrome encrypts our username and password with a secret key or a private key which is only known to our device, which contains very valuable information. Then it sends a very obscured copy or a very less detailed copy of your data to Google. So you can imagine that if all the cryptographic engines or functions stopped working for a day, so the modern life will stop. So bank transactions wouldn't run through, and many people might hack into other people's private messages, and our credit or debit cards passwords might be hacked. So you can imagine it. So nowadays, armies use a method called as the brute force method to crack open codes. So it may be done in the form of programming or codes. So in this, people use one code after another until trying all possible combinations until they reach the correct code. And voila, they crack open the code. So sometimes even some people who want to hack into our private information use this method. So to secure that, OTPs are given. So under the time limit of maybe 59 seconds, OTPs will be sent to our phone. They may be 6-digit or 4-digit. So a third personality might have to try it for a very long time to break open a code which is about 6 digits. So by the time we could have sent our OTP, we could have typed in the OTP. So let's see the relationship between mathematics and cryptography. So the permutation theory is used in cryptography, and the number theory is also used. So it basically explores the properties of numbers in cryptography and factorization. So business computer networks use this method of factorizations. So business computer networks hold information of transactions or business information. So they are encrypted using factorizations of very large numbers. So the key to their network will be the factorization of a very large number. So the unique factorization for that huge number would be the key to the business network. So let's see about two cool facts. So there was a cryptologist called as Alexander de Agapev. So cryptologists are person who create cryptographic codes. So in 1939, he wrote a book called as Codes and Ciphers. So he included a few challenge ciphers in the behind of the book for some people to try to solve those codes. But one major problem occurred. He himself forgot the key to the codes, and till this day, no one knows how to translate them. So it was cancelled out of future editions from his book. So it's a mystery. And then, so this is a puzzle I would like all of you to solve. So on April 1893, Sir Arthur Conan Doyle, you might be familiar with him. So he published his book called as Sherlock Holmes, The Adventures of the Glorious Scot. So he published along with a book called as The Memoirs of Sherlock Holmes. So he used the steganographic messages in this book, in this story. So the steganographic message simply read, the supply of game for London is steadily going up. Headkeeper Hudson, we believe, has now told to receive all orders for flypaper and for preservation of your hen pheasant's life. So anyone wants to try to decode this message? Yeah, you can raise your hand. Yeah, so.
Was Enigma considered between Enigma and Purple, which was considered superior? I know Enigma is widely known as the best.
Sorry to interrupt, Smayan. Is it if it's a Q&A, we can take it towards the end. This is actually the answer for, he's asking the answer for this puzzle.
Okay.
Yeah. Bhagat, I think you can move ahead.
Yeah, so the message simply read, the game is up. So Hudson has told all. So the other sentence was fly for your life. So it led to the death of another protagonist in this book. His name was Trevor Senior. So it was that deadly, this simple message. So let's see the summary. So in this talk, we basically discussed about what is cryptography, the history of cryptography, how is it used, and relationship between mathematics and cryptography. We also discussed some cool facts. So thank you. Any questions?
Thank you, Bhagavat, for that wonderful presentation. And the last slide was an icing on the cake. So those of you who have questions, please do a raise hand and we can unmute you and you can ask your questions. Right, starting with Siddharth.
I have two questions. I have a question and a comment. Can you go back to the previous slide? A previous slide? Okay, the thank you slide, basically. The thank you slide. Okay. So in the thank you side, I saw cryptographic message 28 114 11
Yeah.
That I think that's cryptography for thank you, and 00 means space.
Yeah. You're right. Yeah.
Okay, so here's my question. Can you repeat what's asymmetric cryptography?
Yeah, sure. So basically, you can imagine it as like there's a home and there's a letter box outside it. So a postman delivers a letter. So he opens the shaft and he puts the letter in, but he cannot access other information without the key to the lock. So only we have the key to the lock. So we open it from the other side and access our information along with the letter. So what the postman is, he is the sender. So you can imagine him as the sender, and we are the receiver. So the sender uses a public key, which is acts. So he can send messages to anyone he has contact with, and also the receiver has contact with. But then he cannot access the files or bank transactions of the receiver. That only the receiver can access. So basically, the receiver uses his private key to open the
Okay, so basically the sender can only encrypt the message. The sender can only encrypt, but the receiver can both encrypt and decrypt.
yeah, you're right.
Okay, but I haven't ever seen an example of this with private key and public key. Not very familiar with that.
So we don't encrypt it. So when it's let's take
Hello,
yeah. So am I audible?
Yes.
Bhagavat, I can't quite hear you.
Bhagwat, I think it's an issue with his connection, but you can explain.
Sir, am I audible now?
Yes, you are.
So we don't encrypt it. So when we send it across through WhatsApp, so let's imagine it as WhatsApp, and so the it automatically gets encrypted, but from our side. And then while it reaches the receiver, it automatically gets decrypted from the receiver side using his own private key. So he doesn't know that it's being encrypted or decrypted.
Right. Thank you, Bhagwat. Kashyap.
Yeah, sir. I have a question.
Go ahead.
So, like, I have a question for Bhagwat, sir.
Please
So,
go ahead.
In his the first one, like, I forgot the name of it. So in there you said he said that both the sender and the receiver have access to the same key. So will that be safer than the other one?
So no, the symmetric key, according to my, so I think that I personally think that so the asymmetric key cryptography is better than the symmetric key cryptography, because they both will share, the sender and the receiver will share the same files, and maybe the sender might have evil intentions or something like that, and he might also try to hack the files which the receiver has. So I consider that the asymmetric key cryptography is more safer, much safer.
Okay, thank you.
If I may just add on to that, so if anyone gets the cipher to the symmetric key cryptography, they can decode it, right, Bhagavat?
Yes, sir.
Right? So
it's not basically the cipher, so it will be a key. So suppose if I'm converting alphabets, so hello, in like I said in the first slide, so into a long series of numbers according to their alphabetic positions. So a person needs to have the key to it. So he'll write down A, B, C, D, F, G until Z, and then he'll number it. So if he has that key, then he'll be able to decipher it.
Right. So that's what I meant. Yeah. So cipher is not the right word. So he needs to have the key of how to, and whoever has the key has the access to the information. So it's less safe in that sense.
Yes.
Right. Okay. Yes. Bhuvan.
Yes, this is Sangeeta along with Bhuvan. Bhagwat, it was an excellent presentation. I just wanted to add one more information. That is, you might have also come across CAPTCHA, the image captchas. That is also one form of visual cryptography. So I just wanted to add that information. That is also, since you were pointing out about Alan Turing, this is also the earliest of the algorithms for this was developed by Alan Turing. And this CAPTCHA basically means completely automated public Turing test to tell computers and humans apart. Because these days, many algorithms are there, or probably like the smart bots, which can second like a human and make entries. So to prevent that, we have this CAPTCHA mechanism. So this is only an info. It was an excellent talk. Keep it up.
Thank you.
So, if I may just ask, sorry, it was Sangeeta, right?
Yes, I'm Sangeeta.
Yes, Sangeeta. So, would you have any idea why these days the CAPTCHA is coming? It's more to do with identify trucks and road crossings and traffic signals and parking tickets. And earlier it was not the case. So, is it something to do with getting data from the users? Because
yes, it is
auto driving cars are
that is mainly because now AI is coming into a big way. So more the data is there. Actually, all these algorithms are capable enough to detect from even by image recognition, object recognition. All these algorithms are capable of detecting. So to make out, we actually need more information to be mined from that available data. So which is anyways not possible by the existing algorithms, which is not in a way matching the human capability. That is why that CAPTCHA is being now coming in a big way.
Thank you.
So sorry, I have a because in it it's an interesting thing. So this this CAPTCHA thing is for the security purpose as well as for getting data from collecting data from the users for the sake of AI. Not data, exactly.
It is
information.
Not basically to collect the data. It is to know whether a human is trying to access the data or it's the algorithm. Because algorithms are now coming in a big way and they are able to manipulate the data.
Right.
From because there are lots of images available. From these images, the low-end algorithms itself are able to find out mine information and use that information in the wrong way.
Yeah, got it.
Yeah, thank you.
Thank you. Sarvesh?
Yes. So CAPTCHAs are basically like to identify if we are bots or robots, right? I mean like humans, right?
Yeah.
Is that a question, Sarvesh?
Yes.
Okay.
Yeah, thank you.
Johan?
Okay. Bhagavat, if I had an OTP and a hacker, a 4-digit OTP, for example, it only needs 24 combinations. There are only 24 possible combinations. Okay, if a hacker had access to this OTP, okay, so if I had left it enough time, would the hacker be able to crack the OTP and then like access my info?
So it basically depends on the seconds the OTP is giving. So if it's if it's about 59 seconds, so you're saying like about 24 combinations, right?
Yes. No, that's only if you have a certain given digits. If only if a hacker knows what digits are there in the code. Otherwise, you have lots of digits.
Yeah. So it's basically upon only the number of digits are given. So it may be 6 digit or 8 digits.
You have 100 combinations in if you have a 4-digit thing. So if you leave it for around 10 minutes, because one of the OTPs it stays for 10 minutes, would he be able to crack it?
So basically, so if it's for 100 combinations, maybe he can use, maybe he can program any software, or might be the chance that even if it's 59 seconds, he can decode it even if it's a 4-digit number. So it's based upon how fast the program can go.
But what if it's 2400? Then it would not be able to do it, right?
So he might give the program like based upon the number of digits. So if it's he might not know the number of digits. So when he hacks into it, if he finds it's 4-digit and he has 6-digit programmer, then he'll take a lot of time to do it. So if he's programmed it into 6 digits, and then even if it's really 6 digits, then he might crack it. Yeah.
So but if he had a 4-digit thing and he had to and then he knew that the digits would be from 1 to 9. Then he had a program for 4 digits. Would he be able to crack it before 10 minutes?
Yeah. So can you repeat again?
Okay, so right now there are 2,400 combinations for just four random digits between 1 and 9. Yeah. That is including 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So if there was an OTP that would last for 10 minutes before resetting, would a hacker using a program for 4 digits be able to hack into the OTP and take your data?
It might depend upon how much fast it can go. So if the program is very fast, he might be able to.
Okay, so how fast is the fastest program?
So that I'm not that much sure. So I'm not.
Okay.
I'll research and let you know.
Okay.
Sai Charan, you have a question?
Yes. So can you hear me?
Yeah.
Yes.
Yeah, you were speaking about CAPTCHAs, right? You said that it's to differentiate between humans and robots. Why? I just have this doubt. Why can't robots understand CAPTCHA?
So basically, I think so. I think so. Under my impression, I think so. Basically, the robots are just maybe. I'm not sure. So maybe the robots may be just programmed to hack into it. So they might. So if they come in the obstacle of CAPTCHA, so they might not know how it is. But if they're programmed to identify these, then they can cross the hurdle of CAPTCHA.
Okay. So we have a few more hands raised. Let me just take one more and then we'll move on to the next speaker in the interest of time. And others, if you have any question or response, you can put it on chat. Siddharth?
Okay. So here is my last doubt.
Yeah.
Okay. Okay. So it's again related to the OTPs. Okay.
Yeah.
You said that hackers can use brute force method to crack into codes. Brute force method. Yeah. And actually, I think I have a doubt about it. Yeah. Surendran, okay. So if there are many, so Johan's question was basically the answer, and okay, I need to, okay.
You got your answer.
Got my answer basically.
Okay. Thank you, Siddharth. The others who have raised hand would request you to kindly excuse me. Okay. Bhagwat, can I stop sharing your screen?
Yes, sure.
Okay. So thank you once again, Bhagwat, for that wonderful presentation. And you covered the field of cryptography in quite detail. And I love the part of the history of cryptography, of how it started and how you went about it. So my question, just one quick question to you, and then we will move on to the next speaker, is how did you get interested in this topic of cryptography? If you can share something on those lines. Yeah, that's it.
So, sir, I had this book of the Memoirs of Sherlock Holmes. So I read the Adventures of the Gloria Scott. So I got interested in that message. So after that, I left it. Then I read a book called as Magic Treehouse Fact Tracker. So in it, about World War II. So in it, it was mentioning about the cipher device called as Enigma. So I got more interested in it and I researched on the fields of Enigma, and then I moved on to cryptography and steganography.
That's wonderful. Bhagwat, keep it up and keep reading and learning more about the subject. Wish you all the best.
Thank you, sir.
Moving ahead to the last speaker for today, Vagisan, can you switch on your video? Yes. So it gives me great pleasure to introduce Vagisan. So Vagisan is part of our Ganit Manthan program. He is 11 turning 12 this year. He is from Chennai, and Vagisan basically loves everything. So he has varied interests. He loves history, geography, linguistics, coding, music, math. Needless to say, he loves public speaking. He loves poetry. He loves Pokemon, Minecraft, Discord, and so on and so forth. So he is fascinated about a lot of things, and he loves learning basically. I need to mention a couple of things before I hand it over to Vagisan. So Vagisan got an honorable mention in the Linguistics Olympiad at international level this year. So that's a very hard nut to crack, the Linguistics Olympiad. In case some of you did not know that there is an Olympiad on linguistics, you can check it out. And he also won the first prize in Geography B at the Asia Pacific level. I didn't know that there is a Geography B, like a spelling bee contest. And if you want more details, I'm sure you will get it over the internet. He is an active member in our Ganit Manthan class, the Kaprekar batch, and he was also part of the Epsilon India Camp 2021, which is a camp for students who are highly passionate about mathematics. So that's in short about Vagisan. Vagisan, over to you. You're on mute, Vagisan.
Thank you, sir, for your kind introduction. Hello all, this is Vagisan and I'm going to present about lucid linguistics. So first, let's look at let's think about, is linguistics similar as learning languages? Let's find out. So first, let's look at what exactly is learning a language. When we learn a language, we usually do speaking, reading, listening, and writing. And also, like when we start learning the words. Then we learn to and the sounds and the alphabet, and then learn to put them together into sentences, and then start communicating in a language. Okay, now let's look at what exactly is linguistics. So linguistics is basically a scientific study based on logic, and linguistics does not need to learning languages to happen and to be learned. And linguistics is rather a systematic study of sounds, words, sentences, and where we dissect the language into its basic components like these. Okay, let's look at the different areas of linguistics. Here is a chart showing all of them. Let's move on to the innermost circle, phonetics. Phonetics is a study of speech. Phonetic is let's take the word cat. The vowel inside the word is a, and a is pronounced in the front of the mouth, and it's not pronounced like a or o or a. So yes. So now let's look at another type of linguistics. It's phonology. Let's take an example of phonology. So let's take the words cat and cot. So what's different? There's only one sound which is a distinct sounds and not the same forms of the same sound. This is called as phonology, and it's the structure of the is the study of the sound structure of languages. Okay, now let's move on to the purple circle, morphology. Let's take an example of morphology. Let's have the word activation. This is none other than the word act plus 3 suffixes if plus 8 plus shan. So as you can see in the bottom. And so the next, and so it is the study of the structure of languages, the word structure. Syntax is even different. So let's take two sentences in two languages. I go to school and मैं school जाता हूँ. So in both of these, the word order is different. So if we literally translate both to English, it is I go to school and I school go. So what happens is that both the languages have different sentence structures. So syntax is the study of sentence formation and structure. So let's move on to the orange circle, semantics. So let's take an example. So we usually go to school. So when we go to school, and so when we hear the word school, we usually visualize a classroom, a blackboard, and so on, based on the experiences we have had in the school. This is semantics. It's the study of meanings, the literal meanings. When we hear a word, what we think of, that's the meaning. Okay. So the last circle, the yellow one, is pragmatics. So pragmatics is the study of meanings with context. Let's take an example. Let's say I say that I was a busy bee. But saying that I was a busy bee does not mean that I have wings and I can sting. So it means I was as busy as a bee. Do you get it? So there are 6 areas of linguistics, as you can see here. Okay, but we have not still learned what are the purposes of learning linguistics. Let's move on. So why do we study linguistics? The first thing is to understand what's going on in their mind when they are speaking a language, and what's going on in their mind when they're learning a language. So we need to understand how people acquire and learn a language. So that's one aspect. The second aspect is to understand the intricacies of the world languages and get fascinated by it and understand them and appreciate them. And the final thing is that to understand how languages change over time. This is also something very important. The English language may change in the future, so we need to take care of this. So now let's move on to the practical applications of linguistics. So how is linguistics applied? So let's look at the first thing. So linguistics has made people decipher even ancient languages like the hieroglyphs, which is actually which actually represents the Egyptian language, and so they were able to understand the Egyptian language. Another thing, and they also could understand the language and found that it was similar to Arabic, which is spoken in Egypt today. Let's move on. So linguistics can also help people with speech problems, because first speech sounds are actually just phonetics. So linguistics will definitely help them cure their speech problems. Linguistics can also help us understand the history and culture and the evolution. One example is that the Tamil people had actually traveled to Korea, and and we can also, there are also linguistic similarities. Then we can also translate if we are good at linguistics. One example is the visit of the Chinese president in Mahabalipuram sometime in recent years. So there were interpreters who were sitting next to both the president translating the languages like Chinese and Hindi. Okay, last but not the least is something you have in your day-to-day life: natural language processing. This has actually helped the creation of Google Assistant, Alexa, Cortana, and Siri, and even the text-to-speech and speech-to-text recognition softwares. And this has also been able to make robots speak the language by making models of the language structures, and so they were able to linguistics. Now, it is not compulsory for you to know a lot of languages to do linguistics. So, in order to do that, like I have created a made-up language called the Vichari language, and so the language is also named after the Vicharvatika. Okay, so this is the think about the puzzle. And so the puzzle is Ro is mother, Roro is maternal grandmother, and Faro is paternal grandmother, and what's paternal grandfather? Okay, let me give you the solution. So we know Ro is mother and Roro is mother's mother, because Ro is repeated twice, so it has to be mother, mother. And it also can express the concept of a maternal grandmother. So Faro is, we know it has two parts, Fa and Ro, and we already know Ro is mother. And the thing that connects paternal grandmother with mother is father. So we can reduce Fa is father. So the paternal grandfather, which is father, father, has to be Fafa. You all got it right. Okay, let's try another puzzle. Here are some numbers in the Vichari language. And you have to understand you can understand the structure of the numbers, and you can answer these questions. I'll give you 1 minute. Okay, so let's look at the answer. So we know 1 is V and 10 is day. And we also know 20 is po day. So po day is po plus day, and 10 is actually the And so Po has to be some number which gives a relationship between 10 and 20. So Po has to be 2, and the prefix to 10 has to be multiplication. So let's look at the next number. So we had 11, and 11 is Devi, and so Devi is 10 1, as we can see here. So any number coming after 1 has to be addition. Now we see another one. 32 is Mude Po. So 32 is actually we know it is something 10 and 2, and we know that the suffix is addition and the prefix is multiplication. So we can deduce Mu as 3, as Mude Po is 3 10 2, and it's 3 times 10 plus 2. So now let's look at the solution of the problems we have. So we know Mude is 3 times 10, so it is 30. Depo is 10 plus 2 actually, and it's 12. And these numbers in Vichari are 21 is actually a Po Devi, so it is 2 times 10 plus 1, 2 10 1, so it's Po Devi. The same way we can substitute 1 with 3 and we get Podemo 23. Okay, here's another problem you can try. So Ko is house, Hoko is hospital, Kona is family member, and Chaco is school. So try these translations, and time will be 1 minute. Yeah, time up. So now let's look at the solution. So let's move on. So we know Ko is house and Hoko is hospital. So what can Hoko be? So what can Ho be? So Ho is actually sick. The same way we can do for Kona. And so Kona equals to Ko plus relationship between family person and house. So Na has to be person. The same way we can try Chaco. So as it's the relationship between house and school. So this is the vocabulary we have. So we know Ko is house, Na is person, Ho is sick, and Cha is learning. So let's look at the translation. So first, student. Student can be explained simplest as a learning person. So it's Jana. B, doctor is a hospital person, like you have Hoko and Na, and so it has to be Hoko Na. So let's look at the translations from Vichari to English. So A is actually Hona, and when we translate Hona, so we have patient as it's a sick person, and the same way we can translate Chakona. Chakona can be is Chako plus Na, school person, or not to be confused with Cha plus Kona, which is a learning family member. So Chakona is a school a teacher. So now that you have solved a lot of problems, I'm gonna solve one for you. So this is the puzzle, and so let's start solving them. So we already have some known vocabulary, so we can construct the words we already did in the previous problem. So we can mark all those words. Now we have the compound words here. So first we know Ro is mother, so let's cancel that out because we need to find the unknown words. So then Fa is father, so we don't have it alone, but we have Fa, so we can cancel. No, yeah, we have Ko. So Ko is house, so we can cancel that out, marking this, followed by Ho and sick, then Hokon, Chako and dog school, then Hokona and doctor, then Hoko and hospital, then Chana and student, and Fafa and paternal grandfather. I think we have got all of these words right and we have mapped them. So let's look at what we don't know so we can solve those. So we don't know the meaning of ki, ma, and li. So we know, so let's attack the word ma. So let's attack this part of the problem. So ma puzzle. So ma is goes to, and the simplest sentence is hokona hokoma, and the last word of the sentence, which is ma, is the only missing word, and here goes to is again the only missing word. So we can cancel that out. The same way we can do it for Li. This is the only missing word in both of them, so we can cancel that out. The same way it's Gi comes to, and it's the only missing word here, so let's cancel that out. We are done. And the only other thing we don't know is the grammar. So let's try to figure out the grammar. We may see that all the verbs are coming in the end, right? Ma and Gi. So we can say that all the verbs come in the end, and also the subject. So first let's take the first sentence. We have Ro, then Li Chako. So this is the subject and object. So we can reduce the word order as subject, object, verb, and then we also have some adjectives. So we see that Li Chako directly maps to old school. So we can say that adjectives describe the word they precede. Okay, so here is one problem, one question regarding the puzzle. So we have all our grammar and vocabulary here, which will help us. So let's take this. Sick old maternal grandmother comes to the old hospital. So just like Fafa is paternal grandfather and Fa is father, so Ro is mother and Ro is maternal grandmother. So this is the only word not there in this vocabulary. So using that, we can also like use the meanings of these words, and so we'll just check, map the meanings directly. So sick is ho, old is li, maternal grandmother is roro, comes is gi, and old is li, and hospital is hoko. So now let's put it together. Holy roro giri hoko. But this does not sound like vichari. So we need to let's do subject object mode. So holy roro is the subject, li hoko is the object, and gi is the verb. So we get holy roro li hoko gi. Yes, we did it. So let's move to the next slide. Okay, so let's look at exactly what some of the important things we learned. So linguistics can be learned without learning languages. Linguistics is a study based on logic, and it is, I hope you start trying linguistics. And if you love the session, here are some opportunities you can use. So we have, you can attend the Panini Linguistics Olympiad. So the Olympiad is there in all 3 levels, from India level to the Asia level to the world level. So you can try that. And you can also find a lot of puzzles and resources in the website of the Panini Linguistics Olympiad or the PLO. So you can try those. They are the ones from the past PLOs. And also you can check these YouTube channels, Native Lang, Lang Focus, and Kidnap. So let's move on. So if we can collaborate, you can email me at vakisen.surendran@gmail.com. So I hope you enjoyed the session and liked the presentation. So thank you. If you have any queries and doubts, you may raise your hand, please.
Thank you, Vagisan, for that amazing presentation. Now, for the first time in my life, I could experience what it means to create a language. Right? I mean, we get a language for free that somebody has created and sell them. Not somebody, which may have evolved over a period of time, but then there have been so many linguists in each of these languages, right? Who created the structure, who put a very good frame to it, and that is why we are able to use all of them for free. So I could see how much of effort they would have put in, especially in the last part when you did that translation, word to word, and then you went to the grammar structure. So that that is something that we cannot miss out. It has to go both translation as well as the grammar structure. So it was a wonderful presentation. Thank you, Vagisan. And let's see the questions that have come up. So starting with Adrit, and anyone else who has a question may please raise your hand. Adrit.
Yes, sir. What I wanted to ask Vagishan is, how did he learn so many languages so quickly?
Like me?
Can I just add on to something that Adrit said? Adrit, maybe we should ask a question prior to that. How many languages do you know? Right? And then how did he learn? Yes, Vagisan.
So simply the answer is 2. So actually I'm fluent in only 2 languages, like my mother tongue and English. So I'm not fluent in like the other languages. I may know like little bit of each and kind of, yeah. So
okay.
Do you have any other extra questions?
No, not exactly. Thanks
Okay,
a
so
lot, Pagisan.
Vakisan, you said you know a little bit about other languages. So can you elaborate what is that little bit, in terms of understanding a language? Is it speaking, writing, reading, and how many different languages do you know in terms of those little bits?
Okay. So in those little bits, some languages, like even though I can't speak it or read it fully, I may understand exactly how it works. Like sometimes I understand like that, and sometimes I may automatically know words in other languages even without me learning them. For example, I may know lots of Korean words if I know some amount of Chinese, and if I know some amount of Hindi or Sanskrit, I'll know a lot of Thai words. So actually, like that, I can so I also have a coin collection, and I saw many kind of and where Korea borrowed from China, borrowed words from China, so I could easily map them. So I knew little bit of them. So that was one thing, and another thing that I know to read and read the writing systems of many lots of languages. Actually, no one can know all the Chinese characters, but I know to some reasonable extent, and other than that, I know various like it starts from English, Spanish. So I'll have to count a lot. So English, Spanish, Polish, Czech, Slovak, Serbian, Hungarian, Russian, Latvian, Greek, Turkish, Albanian, Persian, Arabic, then Punjabi, Sindhi, then Marathi, Gujarati, Kannada, Telugu, Malayalam, Tamil, Bengali, Hindi, then Burmese, Thai, Lao, Indonesian, little bit of Japanese, a reasonable amount of Chinese, then Korean, then yeah, I think
That's it? Only
yeah.
these many?
Yeah.
So that's so wonderful, Vagis, and I bet you cannot say all these languages in one breath. And if you do that, maybe you cannot name these languages in one breath, right? So that's really amazing to see how you
And
you thought
actually,
of it. Go ahead.
I checked the web watch. I checked the chats, and it says do you know anything about Arabic? So actually, I can read what's written here, but I may not know the meaning. So so what is written here is Shukran, and I think it's the source for the Hindi Shukriya. So yeah.
Shukran, probably. Yeah. That's great. That's great, Vagisan. Amazing. So looks like there are no other raised hands. So let me just add one question. And if anyone else has any questions, please do a raise hand. So Vagisan, all this love for language, it with your coin collection? Is that how it started?
It has started like so. The coin collection was like one of the sources, and actually it made me do a lot of. I so analyzed the coins linguistically rather than just having it as a collection. I used it as an opportunity for linguistics. So what I did is that let's say I had one coin from Taiwan, and I read what was written in Chinese, and it told like is these many years. So it told like a certain number of years. Then I calculated it, and then I saw the date of the Chinese Revolution. So I saw interesting things like that.
I see. Okay, and is that how it started? That's my question.
Like that was one of the things like where it started, but actually in the computer, like there is an app called Character Map. So I was also like interested in exploring everything in the computer. So I took the Character Map app, and so that made me a fascination to read and write all this so many symbols. So like so that's where it exactly started.
Very interesting. You know, I had a coin collection, and I would just count the money and be happy for how much ever money I had. Wish I could go further than that. All right. So Anupama, question.
Yes, sir. To Wagi sir, have you ever tried making a conlang then?
What did
Have you ever tried making a constructed language?
No. So this was like the first time I tried, but I have tried, but like I immediately stopped. But this was like the first time I really made one.
Okay, thank you. It's a little complicated.
It is really hard to make one.
Thank you.
So how much time did it take for you to make this Vichari language, Vagisan?
Like totally, it must have taken an hour.
In 1 hour, you made this language.
In 1 hour, I could make this much grammar and vocabulary, and
wow.
Yes.
Okay, that's really cool. That's really cool, Vagisan. So Vagisan, there is one last question before we conclude the session. Do you have any role model, any hero when it comes to linguistics?
I don't have anything like specifically, but I have some specific role models. So my first role model is actually like Wikipedia. I browse a lot of Wikipedia on linguistics, and yes, so that's one of the kind of role models. And also I watch some YouTube channels on linguistics, so that's what actually they are
All
very
right.
interesting.
All right. And what's your plan ahead in terms of learning languages? So where do you want to go ahead with it?
I don't know.
You just enjoy learning languages, right?
Yeah, I just enjoy.
Yeah, beautiful. All right. So I think we can take a pause here. Thank you so much, Vagi. And we could see your passion for language, and it was really amazing how you brought the idea of logic to learning languages, because at least when I was in school and college, I never thought that you can learn a language using logic, because language and logic seem to me like on opposite directions. So you threw that fascinating aspect open to us. So thank you so much for that. And we could see how much effort you have taken to assimilate all these, to collate all these information that you had in your mind about languages. That was a really well made presentation. Thank you so much. And I would like to thank once again all the three speakers who have who have delivered these talks today. And to the audience, I have to tell you that I've seen them how much hard they have worked over the past 1 month. And some of them, they did takes after trying to understand how you can squeeze everything to 12 to 15 minutes, because they are so passionate about the subjects. As you can see that they had a lot of information with them, and it was very hard for them to bring it down to a short span of time. And I said we need to have a hard stop at 15, and all three of them did a lot to confine it to 15 minutes. So I think we should really appreciate all the three speakers of today. And to all the audience who joined in, my sincere thanks to all of you for taking out your time on a weekend, especially like this. We hope to see you for the future sessions as well. In case you haven't seen the earlier talks, I would encourage you to just have a look at our YouTube channel, and then you'll be able to find the links for the talks. I'll also put it here on the chat. What I've also done is some links that Vagisan had shared. I've put it on the chat. So those of you who loved languages, you can have a look at this, and do subscribe to the YouTube channel so that you can keep getting notifications of such videos in future. So my thanks to one and all once again for taking out your time. Looking forward to see you on the last Saturday of next month. Thank you. Stay safe. God bless all of you. You can post your comments to the speakers on the chat, and I'll request Bhagavat, Vagisan, and Johan to stay back. And if their parents are also there, requesting them to stay back. Others, see you next.